Hello all, welcome to my research paper, Comprehensive Exploration of the Archimedean Property, Insights and Proofs for Undergraduate Mathematics Students. I am B. Tabsum, Assistant Professor, Department of Mathematics, Government College of Arts, Science and Commerce, CAPM, Goa. The abstract of my research paper is, this study has been undertaken to understand the Archimedean property in detail. Various references have been made to go in depth of the concept. An attempt is made to combine all possible results on the Archimedean property so as to help the reader to have a better insight of it. The aim of this paper is to explore maximum number of statements with proof that can help the undergraduate students studying mathematics to understand this property in a better way. Index terms, field, greatest integer function, supremum, least upper bound property. Introduction. The Archimedean property is named after the ancient Greek mathematician Archimedes of Syracuse. One of the fundamental properties of the real numbers is the Archimedean property, an axiom introduced by Archimedes in his work on geometry. In modern language, it says that every real number is bounded above by a natural number. For any x belonging to R, there is a natural number n, so that x is less than or equal to n. It follows that there are no infinitesimally large or small elements in R. That means every element in R is bounded. The property states that given two positive numbers x and y, there is an integer n such that nx is greater than y. For example, if x is 7 and y is 100, then we can find a number n is equal to 15 such that nx is equal to 15 into 7 equal to 105 greater than 100. If x is 4 and y is 179, then we can find n is equal to 45, that is n into x, that is 4 into 45 is equal to 180 greater than 179 equal to y. If x is 100, y is 7, then we do not have to find any natural number because x is as in greater than y. Therefore, your natural number under consideration is 1 over here. In case x is 179 and y is 4, clearly x is greater than y. So the natural number that obviously exists is n equal to 1. Since we are doing for positive integer or real numbers, so we consider only positive real numbers. There is no picture of negative real numbers over here. Now the question is, how did all these natural numbers came into picture, that is 15, 45, 1 and 1. So the idea behind is nx should be greater than y, and therefore we want a natural number greater than y by x. So y by x can be a fractional number, or it can be a real number, or it can be a rational number. So in that case, since we want a integer and a positive integer, we can take the greatest integer function of y by x, which is always going to be an integer. And in that case, if it is 0, then we will put plus 1, so we are getting a natural number. In case of any kind of any other integer, obviously since y and x are positive, y by x is positive, and therefore we are landing with a positive natural number. So some of the properties that we have listed and we have proved over here is, I have listed the subset n of natural numbers is not bounded above in R. Second property, if x belongs to R, then there is a natural number such that x is less than n. Third property, if x and y are both positive numbers, then there is a natural number such that x is less than ny. And if y is a positive number, then there is always a natural number such that 1 by n is greater than 0 less than y. If x is greater than 0, then there is a natural number such that x is greater than or equal to n minus 1 less than n. There exists a positive real number x such that x square is equal to 2. The density theorem, that is rational numbers are dense in R. If x and y are real numbers with x less than y, then there exists an irrational number z such that x is less than z less than y. Property number 9. If x is greater than or equal to 0, less than 1 by n for all natural numbers, then x is equal to 0. If a and b are two real numbers such that a is less than b plus 1 by n for all n belonging to n, then a must be less than or equal to b. If x is a real number, then there are integers p and q such that x lies between p and q. If x is a positive real number, then there is a natural number such that x lies between 1 by m and m. Between every two rational numbers, there is always a rational number. Between every two rational numbers, there are infinitely many rational numbers. Between any two distinct irrational numbers, there are infinitely many irrational numbers. Property number 16. Between any two distinct irrational numbers, there are infinitely many rational numbers. Between any two distinct rational numbers, there are infinitely many irrational numbers. For any positive real numbers, there is a natural number such that 1 by 2 to the power n is less than y. 0 is the infimum of the set 1 by n such that n belongs to n. If x is a real number such that n absolute value of x is less than 1 for all n belonging to n, then x must be equal to 0. For every epsilon positive, there is a natural number such that 1 by n is less than epsilon for all n greater than or equal to m. There is no rational number such that x square is equal to p, where p is a prime number. Let x and y are any two positive real numbers, then there is an integer n such that nx is greater than y. The conclusion. The Archimedean property is a fundamental concept in mathematics that states that for any two positive real numbers a and b, there exists a positive integer n such that na is greater than b. In other words, it states that no matter how large a real number is, there is always a multiple of another real number that is greater than it. The Archimedean property has numerous applications in various fields of mathematics, including analysis, number theory, geometry, limits and convergence. The Archimedean property is essential in the study of limits and convergence of sequences and series of real numbers. It is used, for instance, to prove that the sequence 1 upon n converges to 0 as n approaches to infinity. Calculus. The Archimedean property is used in the definition of real numbers, which is the foundation of calculus. It is also used in the study of derivatives and integrals. Number theory. The Archimedean property is used in the proof of various number theoretic results such as irrationality of pi and the existence of infinitely many prime numbers. Geometry. The Archimedean property is used in the construction of geometric objects such as polygons and polyhedral. It is also used in the study of properties of circles and spheres. In summary, the Archimedean property is a fundamental concept in mathematics that has far-reaching implications and applications in many areas of mathematics. These are the references that I have used. Thank you.